When you have questions that require you to work out either the area or dimensions of shapes, one such shape that may be involved is a sector, this being this wedge-like shape here. Now these you may have come across in GCSE as being a fraction of a circle. If we were to continue these all the way around, it would make a full circle. But here we're going to take it a little bit further, not in terms of the actual nature of the shape, because a shape is still a shape, but now we're going to work them out using radians. If you're not entirely familiar with radians or would like a recap overview of them, I would suggest going to the video where we look at how to solve for angles in trigonometric functions, because we discuss both degrees and radians in that, but of course I will also give a brief recap here. Overall though, because these sectors are related to circles, it's probably best that we start looking at circles. So if we have a circle here with a radius of r, the radius being the line from the centre of the circle to the edge, we can say that the area of the circle would be found by pi r squared. And that the circumference, that is to say the length all the way around the edge, or the perimeter essentially, that is either 2 pi r, or if you prefer, pi d, where d is the diameter, and diameter is double the radius anyway. So if we're working with radius, you may as well use that. Just saying, this is also an option. Now if we were to do this for a fraction of a circle, therefore, let's say we just labelled this angle here theta, then the area of this sector would be theta out of 360. Because there are 360 degrees in a full circle, but here we only have theta of them present. So it'll be this fraction, theta at 360, lots of the usual pi r squared. As for the arc length, this being this curve on the outside, the fraction of the circumference, this again would be theta over 360, and then lots of the 2 pi r, that fraction of the full circumference. However, there is another way of doing this, and this is, as you may now guess, if we do it in terms of radians rather than degrees. The equivalent of 360 degrees in radians is 2 pi. So if instead of 360 we were to do 2 pi, we'd have theta over 2 pi r squared. Oh, but here we have a divide by pi and a times by pi, which cancel, leaving us essentially with a half theta r squared. This would give you the exact same value as this over here. It's just that this formula doesn't include pi, so in that regard it's a little bit simpler. All you need is half the angle times by the radius squared. Similarly here, if we were to make this theta over 2 pi times 2 pi r, the whole of the 2 pi this time cancels, leaving us with just theta r. Once again, would give the same thing, but this is now simpler. Of course, as part of this, the angle will be given into radians as well, so it would be some multiple of pi to begin with. But yes, we're going to be using these formulas now whenever we have sectors as our baseline formulas. Having got these, therefore, just the other thing we want to talk about regarding sectors is the perimeter. Before, the circumference was the whole perimeter of the circle. But here, this fraction of the circumference, well, that's only one edge. We've also got these lines here. If this is the centre of the circle, and then this is to the edge, making that the radius, then this other line is going to be the exact same. It's also from what would have been the centre of the circle to what would have been the edge of the circle. And because it's a circle, it's a constant length wherever you have this line. So in general, when you have a sector, these two straight lines are the radius, this angle is theta, your perimeter would be that arc length, that theta r, but then add 2 more, lots of r. Now that we have these formulas, we could just have a go at filling in some details. So let's say, for an example, we had a sector with a radius of 7 and an angle of pi over 8. And from this, we wanted to work out the area. Well, we turn to our area formula, which is your half theta r squared. So the area will equal a half times pi over 8 times by 7 squared. This would give you 49 over 16 pi. The question would likely tell you for the exact form. That would be to say to leave it in terms of pi rather than a decimal, because your calculator would inherently be rounding the decimal because pi is infinite. Alternatively, we could be given some different elements to start off with. We could be told that the arc length is 10 and that the angle here is now 3.5 rads or radians. Now in actuality, 3.5 radians would actually bring this into being a reflex angle. If the equivalent of the 360 degrees is 2 pi, that means 2 pi will be a whole circle, therefore pi is half a circle, the equivalent of 180 degrees. 3.5 is actually just more than pi, so actually we'd be going just over the equivalent of 180. But again, this is just a sketch here. Either way, if the arc length is 10, we can say that 10 equals, then if the equation is theta r, that's going to be 3.5 r. Therefore, just rearranging, r is going to be 10 over 3.5, which will be the same as 20 over 7. And that is pretty much it for sectors in isolation. You may end up finding them as like parts of larger compound shapes. We'll get on to how to deal with those in a second. But to start off with, just looking at these formulas, just looking at how we can take what may have been the original formulas for a sector, but then simplifying them by turning our angle unit into radians, and how we can use those formulas in a given scenario to, as with any formula, rearrange and solve for a missing variable. If we feel happy with that, let's just see how you would get along with an example of your own. So here we have a full circle, but 2 radii have been drawn on, and the major sector, the larger sector of it, has been shaded. You're told that the area of this shaded major sector is 135 centimeters squared, and that the reflex angle is 4.8 radians. And from this, you're to find the minor arc length. So, think about what each of these numbers or phrases might be referring to, what you have to work out, what information you have, and which formulas therefore can connect them. Pause the video, have a go for yourself, and then press play again when you're ready to compare. If we have the area of the major sector and its angle, well, that's 2 parts of the formula for the area. So let's just start plugging in what information we have. 135 is therefore going to equal this, a half times 4.8 times r squared. To get r on its own, therefore, we're going to want to do 135 divided by the half times 4.8, and then this is going to be square rooted to get rid of the square. Putting this in your calculator, you get a radius of 7.5 centimeters, and we know centimeters is the unit because the area was centimeters squared. If we're then trying to find the minor arc length, well, for the arc length, we just need an angle and a radius. We have the radius, but right now, strictly speaking, we don't have this angle, and considering that this is the minor arc length, it is the shorter arc, this is what we're looking for, that's the angle that's needed. What we can say, though, is because all the way around would be 2 pi, and we know this larger bit here is 4.8, that it's going to therefore be for our theta, 2 pi minus the 4.8, and then this gets times by that radius of 7.5. Now, we could put this just straight into our calculator to get an approximate value of 11.12 centimeters. But if the question specified an exact form, we'd need to keep it in terms of pi. Just timesing each of these terms individually by 7.5, therefore, what you end up with is 15 pi minus 37.44 centimeters altogether. That would be the exact form. If we're okay with that, let's then just see what we would do in one of those questions that I just mentioned, the idea where you've got a compound shape that contains a sector just as part of it. So here we have a triangle ABC, and then ABD inside of that is a sector where the radius is 8 compared to this total side length of this triangle here of 11. The angle then being 0.7 radians. So that's all the information that's been given to us here. And then we have this shaded region R that we're going to be finding out some details for. First of all, though, we need to find the length of the arc BD. Well, for the arc length, that's the same formula as what we just had. We can just do that as theta R. So your angle is 0.7, and your radius just of the sector is 8. So timesing that together, you're going to get a arc length of 5.6 centimeters. Next, find the perimeter of R, giving your answer to 3 significant figures. So in this case, this is not an exact form one. We will be getting it to a decimal and then rounding. The perimeter will be made up of the arc length we just worked out, of this line here, and then this line BC here. Let's say we know that the arc is now 5.6. This line here, CD, because we know that AD is the radius, just like AB, this bit is also 8, leaving us with just 3 for this side. As for BC, though, this is going to be a little bit more complicated. And for this, we're going to have to bring in a concept from another topic, which was the sine, cosine, and area of the triangle rules. If you're not familiar with those, you should check out that video as well. But as always, I'll just give a brief summary here all the same. If we have a triangle where we know 2 sides, and you know the angle between them, and you're trying to find the third side, we can use something called the cosine rule. So if I just draw out another triangle here, and just label it like A, B, B, and C, C, where each side and opposite angle are labelled the same letter, just one is lowercase and one is capital, we can say that A squared, so this side squared, equals the other 2 sides squared added together, minus 2 times those other 2 sides, times by the cosine of that opposite angle. In this case, our BC squared is going to be therefore the 8 squared plus 11 squared, because it's for the whole triangle, minus 2 times 8 times 11 times cos of 0.7. You want to be sure here that you've put your calculator in a radian setting, therefore. Previously, because it was just the number on its own, it didn't matter, but now because you're putting the angle inside of a function, yes, it needs to be in radians rather than degrees. So you'd put this into your calculator, and then BC is going to be the square root of all of that, which, let's say to 3 significant figures, you would have as 7.10 centimeters. Adding up all of the sides then for the perimeter, you've got your 5.6, add your 3, add your 7, well, or essentially just 7.1. That is going to get you 15.7 centimeters as your perimeter. And lastly, the area of R, giving your answer to 3 significant figures once again. When you have these compound shapes, when you have a shaded area, the key to getting that area is just think, what is the area of the larger shape? What is the area of the smaller, unshaded shape? And if we just take away the small from the big, that leaves us with the shaded area. So if we can work out the area of the triangle, and then the area of the sector, triangle minus sector leaves us with that. For the area of the triangle, we're once again going to be referring to one of these rules from the previous topic. So here we can say that area equals half AB sine C. To be clear, the A, B, and C don't have to relate to the same A, B, and C from the previous formula. We're just saying, again, 2 sides with an angle between them. So in our case here, the area of the sector, of the triangle is going to be, so half times 8 times 11 times by sine 0.7. Again, we still just want to make sure that we are in radians. This in your calculator to 3 significant figures will give you 28.3 centimeters squared. For the area of the sector, you will then have your half theta r squared, which will be a half times 0.7 times 8 squared. This will give you 22.4. So lastly, for the area of R, we're just going to have our 28.3 minus our 22.4. So that's going to give you an overall area of 5.9 centimeters squared.